Okay, so we are going to have the next talk of the morning session, and the speaker would be Kirone Mallick, and he's going to talk about exact solution for single file diffusion.
Thank you very much. And I would like to thank the organizers for their invitation. So I'm not a mathematical physicist, I'm not really doing integrable theories, but fortunately I fit a bit into the program because I'll talk about statistical physics. So it's going to be a talk on soft condensed matter and stat phys, where some exact results are obtained using integrability. So I want to tell you first about single file diffusion. Single file diffusion is a phenomena which occurs in many different systems, and in particular in soft condensed matter. And a pristine model for single file diffusion is a symmetric exclusion process. So if you consider some small particles in a tube, and which are quite small with respect to the length of the tube, they will diffuse. This is normal diffusion. It means that if you take a particle and you look at its position after time t, it will diffuse as square root of time. Now, if you consider macromolecules in a small, thin capillary tube that are so big that they cannot overtake each other, you will have this phenomenon of single file diffusion, which means that if you have a marked particle and you look at it, it will, of course, jitter away, but it will not jitter as square root of time, but as the fourth root of time. The mean square deviation of a particle here will be in square root of time. The mean square deviation in normal diffusion is linear with time. So you have a fourth root of time appearing in single file diffusion. So this is a phenomenon that people see in the lab, typically in microfluidics. And this is a phenomenon which is quite attractive from the point of view of trying to understand the probability theory behind it. So there are experiments, even recent experiments, which have been built to understand that. For example, in Beschinger's group. So here you have the small capillary. If it's so small that only one green particle can pass at a time and they cannot overtake each other, you will see single file diffusion. If you make it more wide so that particles can overtake each other, you will recover normal diffusive behavior. Okay? So, if you want to understand this phenomenon, a good way to model it is through the simple exclusion process. So the exclusion process is a simple model for interacting particles, where you have particles on a lattice which are making random walks, which can be asymmetric, and the only constraint you have is that two particles cannot occupy the same site at a given time. So you have this exclusion constraint. It is a classical model. There is no quantum mechanics here. So it's a two-body interaction by hardcore, and this two-body interaction makes it into a non-trivial many-body problem. So it's really an n-body problem due to exclusion. If you have reservoirs or asymmetric jumps, you have a non-vanishing current, and it's not a Hamiltonian system, it's a Markov system. So it really makes it almost orthogonal to what we know from equilibrium statistical mechanics, if you want to understand it. So it's a paradigm in contemporary statistical physics, and it satisfies precisely the mantras that Nuno Romao told us 2 days ago. If you remember, I hope you remember, Nuno, about your 5 mantras. So I try to apply them, and I think this model is a good example of this mantra StatMech. So because it's a minimal model, it appears as a building block in many more realistic models in condensed matter, whether hard or soft, but it's also studied extensively in probability, combinatorics, representation theory, and so on, and we'll see some aspects of it soon. Okay, it was in fact invented in biophysics 50 years ago, people who wanted to understand the motion of molecular motors along strands of RNA, but I'm not going to deal about that. But this is a way to convince people that it can be useful to something. Another way to see this model is to, in fact, map it to the celebrated Kardar-Parisi-Zhang equation. The model of particles hopping on a lattice can be mapped into a model of an evolving interface. When you have a particle, you say that your interface is going down. When you have a hole, your interface is going up. And the hop of a particle is equivalent of adding a brick to your interface. So it's a Tetrix model, which in fact is perfectly equivalent to the exclusion process. And in the long range time and space scale, this model of evolving interface is modeled by the Cardar-Parisi-Zhang equation. So you can very well view the exclusion process as a microscopic realization, as a discretization of the Cardar-Parisi-Zhang equation, which is an important equation for evolution of interfaces. So let's now focus on one special case of this exclusion process, the symmetric model, where a particle can hop in both directions with the same probability. So each one is a symmetric random walk with exclusion constraint. And this model was first defined in the mathematical literature by Spitzer in the 70s. And now suppose that we tag a particle. So we put a color on it. It's a classical model, so we are completely allowed to do that. There is no permutation invariance here. All particles are distinguishable. So we tag a particle and we look at it, we monitor its position with time. So of course, because the walk is symmetric, on average, the average position of this tagged particle will be 0. Now suppose that the particle were not interacting. I remove for a moment this exclusion constraint, so particles can overtake each other, can sit at the same site. Then of course, it is a one-body problem, and the variance of the position of the tagged particle will grow linearly with time with a diffusion constant d. But of course, it's completely trivial. We want to go back to the exclusion process, and the major result obtained already 35 years ago, proved mathematically by Aratia, is that if we take now a tagged particle in the symmetric exclusion model, then the variance of its position, the variance, grows like square root of time. So this T14 behavior, and even the prefactors have been computed exactly by many people and put in mathematical form by Aratia in 83. So this is an asymptotic behavior. It's for a long time limit. Okay, so this is a known result, old result, and somehow this could be the only take-with message if you really want to know the basics about the exclusion process. However, so for the KPZ, it would be the high function, but the symmetric case corresponds to Edwards-Wilkinson. So it's a linear case. KPZ is for the asymmetric, Edwards-Wilkinson for the symmetric. Okay, so this is what was known. And people have studied a lot this exclusion process and done plenty of things. But for this precise problem of a tagged particle in the symmetric exclusion process, not much progress was made. What do I mean by that? So I told you about the second moment, the x square, but no formulas for higher moments are known. x4, x6, odd ones vanish, of course, by symmetry. Okay, so this is already one question. We could ask even a more ambitious question. We could say we want to know the distribution of the particle in time. Of course, this was not known. Position p of xt as a function of time, not only asymptotic. Suppose we want to be slightly less ambitious and we are only interested in the long time limit. So for t going to infinity, we could ask some questions about the asymptotic behavior of this probability distribution. And one thing which was proved quite recently by Sethuraman and Varadhan, again, highly distinguished mathematicians, they proved that this position, the distribution of this position xt, satisfies the so-called large deviation principle, which means that if you look at the probability of being at position xt for large times, rescaled by square root of t, the 4 is here only for aesthetic reasons, then this probability is exponentially vanishing in square root of t, multiplied by a function phi of psi, which is in fact known as the rate function or the large deviation function. So somehow this large deviation function embodies the long time behavior of the probability distribution of your tagged particle. So it would be nice to know what this thing is equal to. So what Sethuraman and Varadhan showed is that this function exists. So they prove existence. They gave some bounds for this rate function, but they did not compute it. They did not have the techniques or were not interested in to compute it. Another thing we could ask also is that we started with particles on a lattice. Is there any influence on the initial configuration in the long time behavior or in the finite time behavior of the tagged particle position? Suppose we start with a step initial condition. We pack many particles on the left, fewer on the right, two different densities, rho plus, rho minus. We put the tracer at 0 position. How will it behave with time? Okay, so these are open questions. It has been open questions, and I'm going to answer them hopefully in the next hour or so. So let's show you the results for these exact tracer statistics. I'll go fast on this. If you had non-excluding particles, random walks without interaction, it's an exercise in probability theory. Again, not so easy if you're not familiar with, but still you can do it. So a simple particle, a single particle making an asymmetric random walk on the lattice, you can compute everything. And in particular, you can compute the large deviation function. Here, the scaling is not in square root of t, but t. Okay? And even in this case, you see the large deviation function is not so cute. I mean, it contains square roots and so on, but it's a simple exercise that you can give to your students. Okay, now let's come to the real problem. So the real problem is particles with exclusion on an infinite lattice. And we start with an initial profile with two different densities on the left and on the right. And we put the tag particle on the 0 position. And I call x of t its position after time t. So I'm interested in the probability distribution of this object, or on some more specific behaviors in the long time limit. For example, instead of computing the probability distribution of xt, I could compute the average of the exponential s of xt, where s is a parameter, the characteristic function. Up to some theorems, it would be the same information. If I know the characteristic function, I know all the cumulants, I know all the moments, I can, as a physicist, say that I can reconstruct the distribution. Okay? It's a Laplace transform of the distribution. If I take the log of this, I get the cumulants. Okay? And as I told you, another way of characterizing the distribution of x of t in the long time limit is through a large deviation function of Sethuraman and Varadhan. And in fact, this characteristic function and the large deviation function contain the same information. You can prove, this is again basic probability theory, and I'm flashing through it. You can prove that they're related by Legendre transform. So if you know one, you know the other. If I'm able to compute the characteristic function and I Legendre transform it, I get the large deviation function and vice versa. So, okay, all this information is the same. Okay, the problem with this question is that your tracers is moving. So it's moving in an environment which is evolving. So if you think about fluid dynamics, it's a kind of question in Lagrangian dynamics. And this is always difficult in this kind of problems to follow a particle which is moving, the environment is moving. It's much easier to do statistics in which observables are fixed somewhere. So I will change my problem and trade it into another one in which observables are located in some specific place. And as I showed you before, there is a relation between exclusion and interface dynamics. So I can, in fact, change a bit my mapping from AZ to KPZ and say the following. I have a configuration of particles in my exclusion problem. If I have a hole, my interface is flat. And if I have a particle, my interface is going up by 1/2. It's slightly different from the previous one, but it's almost equivalent. And so in fact, my configuration of particles here has become this blue line. The only thing I have to specify is the overall height of this line. And the overall height here, I specify it by counting how many particles jumped through the first box from 0 to 1. So this is the total integrated current from site 0 to site 1, which I call N of t, which gives me the overall height of this interface. So I have an interface model, okay, with this blue line, and in fact, it contains the same dynamics and the same information as my original exclusion process. Okay. So the only difference with the KPZ interface is just a kind of shift by x/2, where x is the position. So here now I can be interested in looking at the height over a given site x and looking at this height, which evolves with time, but at a fixed position. So now I have a numerable bunch of observables, nxt, which are fixed in x, and which evolve with time. And the trick is, and this is always, it's a simple observation, but very hard to explain orally in front of an audience. You just need to concentrate and sit for 5 minutes in front of a page. In fact, you have this very simple and nice relation. If you have your tag particle, which was at site 0 at time 0, and I call xt its position at time t, well, the probability that your tag particle has moved further than site number x is equal to the probability that the height, this height that I just defined, nxt at time t is negative. So this is, in fact, very simple. You just have to count the number of particles that moved, and because they cannot overtake each other, the particle moves further than x if it pushes away all the particles which were between its initial position and position x. And doing the counting, you get this relation between the distribution of the tracer particle and the probability that the height over x is negative. So somehow, if we are able to do the probability theory for this variable nxt, for all possible values of x, I know the distribution of the tracer particle. I have traded my tracer problem into an interface problem. Okay? Equivalently, you have the other relation. So from now on, we shall mostly focus on this height variable, because we cannot forget about the tracer for the moment. Okay, so now here comes the result. We want to compute the distribution of these height variables nxt for all values of x, and possibly for all finite value of time, or if not, for large times. And in fact, we have an exact formula for the distribution or for the characteristic function of all these variable nxt's for all values of x and all values of time. And here comes the formula. So I take the characteristic function exponential lambda nxt. So this gives me the full statistics, or the Laplace transform of the probability distribution of the height over x at time t. And this characteristic function is rigorously equal. Again, it's not asymptotic, this is exact. It's equal to a Fredholm determinant given by that. So I will just explain in a few minutes what I mean by this Fredholm determinant. But first I explain the terms that enter into the right-hand side. So it's a determinant of a big matrix, in fact of an operator, an infinite matrix. Identity plus omega. Omega is just a parameter in the system which involves this lambda fugacity and the densities on the right and on the left. K, T, and X, if you discretize, you can view it as a big matrix or as an operator. And in fact, it's an operator with a kernel. And here you have a simple function, which in fact has a Poisson-like behavior. So K, T, and X is an operator with a kernel, and the kernel is given by this formula. So for those who are familiar with Bethe-Ansatz, you in fact recognize the Bethe kernel in these guys. It's in fact nothing but the form factors of the Bethe that appear in Bethe-Ansatz. So what this determinant means is that you take the determinant of an operator, which is given by a kernel, and because the kernel is continuous, you can even prove, it's easy, that your operator is trace class. And if you don't like determinants and you prefer traces, well, you always can remember that the log of a determinant is a trace of a log. Okay, so I can compute this determinant by taking the log. So I need to calculate the trace of the log of this operator. The log of this operator, I can expand it with respect to the parameter omega. So I have to take traces of k, k square, k cube, but my operator is trace class, so all these things are perfectly well defined. Okay. So, by the way, I mean, I also encountered infinite determinants quite recently, but the theory is quite old. It's by the end of the 19th century. It's almost 130 years old that people like Volterra, Fredholm, and then Hilbert defined these objects. So these are classical mathematical objects. Okay, so this is a closed formula. And now from this formula, we can extract information about our problem. But before that, we can also go to asymptotics. So this was an exact formula for finite time. If I go to the large time limit, I can prove that my characteristic function adopts a large deviation type behavior, and I can compute the cumulant generating function, or by Legendre transform, I can get the phi large deviation function. So if you do this work, starting from the kernel, you will find an explicit formula for the cumulant generating function in the large time limit for the tracer statistics in the exclusion process. So all these are results, and for people, for the few aficionados, and I know there are some in the room of the exclusion process, these are amusing results. For people who are not exactly in the business, this may look less interesting. So what I decided to do in this audience is to give you maybe a hint on the techniques we used, because the techniques are very much close to the subject of this conference. So before maybe going to the techniques, I'm just... Okay, one thing also, if you like combinatorics, once you know the cumulant generating function, just by expanding with respect to the parameter lambda, you can compute exactly the cumulants and the moments of your height variable in terms of combinatorial objects and partitions and so on. So if you're interested in the details, in the statistical details, and you want to know the fifth cumulant, you can get your formula explicitly. So this is, well, you're right. I mean, what I call probability distribution is the characteristic function. So this is the Laplace transform. This is the closed result. Yeah. The tails, things like that. Yeah, I will come to that slightly later. Of course, this is the things we explored first from our point of view, but I want to maybe stress slightly more about the technique. So I will give you the strategy of the calculation. How do you get such a result? So first, you use something which is called duality. Because here, remember, we have an infinite number of particles, and we want to compute something about some observable, the tracer, the second cumulant, the fifth cumulant of the tracer position. So it seems to be an impossible to manage problem. It's an n-body problem with an infinite number of bodies. So there is one fantastic property of the asymmetric exclusion process. In the asymmetric case, not in the symmetric case, so I'm going now to the asymmetric case, is that there are certain correlation functions in the model which have a closed dynamics. If you try to look at correlations in this problem in a naive way, you will end up with a BBGKY hierarchy. One body functions are coupled to two bodies to three bodies, and it will never close. And we don't want to make approximations, we want an exact result. So I'm not going to close it by force. Okay? So you cannot deal with that. But there is a magic here. If you look at some special tau deformed, where tau is the asymmetry parameter between left and right correlations, more precisely, if you look at correlations of the type tau to the power n at site x1, tau to the power n at site x2, tau to the power n at site xn, all at the same time, these tau power correlations satisfy a closed dynamics. Okay? So they evolve, their time evolution is only among themselves. So your BBGKY hierarchy closes if you consider this set of correlations. So this property is known as duality, and the origin of this property is related to the fact that the exclusion process, in the asymmetric case, is SU2Q invariant. So there is a quantum group invariance of your exclusion process, which in fact allows you to state that these correlation functions evolved in a closed subensemble. Okay? And these are in fact like n-body, but small n correlations, so there are a finite number of correlations. By the way, so if you like quantum groups and you're happy with that, you can go to these references and see where it comes from. Recently, we found a purely probabilistic proof of this fact using stochastic calculus. So you can forget about quantum groups if you don't like them and get this result through stochastic evolution and Markov processes. I'm not going to, in fact, Poisson process. So I'm not going into the details, but it's possible to see things from a different way. Okay. Yeah? Yes, it is fixed, yeah. No, because my variables are n. Yeah, if I want to compute a correlation function, I would calculate average of nx1, average of nx1, nx2, average of nx1, nx2, nx3, for example. These are n-body correlations. Unfortunately, if I mix the dynamics of these things, they will involve higher cumulants. If I take ddt of nx1t, unfortunately, I will get nx1, nx1 plus 1, and so on. But if I take the dynamics of these observable, they will remain closed among themselves. That's the magic. So tau is the asymmetry parameter. It has to be different from 1, so it does not include the symmetric case, which is the one I'm interested in, by the way. But for any given asymmetry of jumps, this is true. But it's fixed in the whole system. Particles can jump to the left or to the right with an asymmetry tau, p over q. P to the left, q to the right, p over q is fixed. It will not work. It's a tau given by the dynamics. That's a good question. If that was a question, yeah. It's a tau given by the dynamics. Yeah. There are some cancellations. So this is the first step, and a priori this has nothing to do with integrability. This is a property of my stochastic model. Okay, now comes integrability, because now I have reduced the problem of computing k correlators to a finite problem with k bodies, because this is a finite dynamics with k bodies. Okay? And now this dynamics, this effective dynamics for these small n correlators, in fact, turns out to be the same, this is duality, as the exclusion process dynamics itself, but with a finite number of particles. So this is the key of duality. You have a closed dynamics for these special correlators, and the dynamics is the same as the exclusion process with small n particles, so a finite number of particles. That's an observation. And the exclusion process is an integrable model. So I can solve it by Bethe ansatz. And even more than that, because I'm on the infinite line, there are no Bethe equations, there is no quantification of the Bethe roots, they can take any value, and you can use exact Bethe ansatz. What I mean is that these functions can be calculated exactly, expressed exactly as some, in fact, integrals, because now you have a continuous, in fact, values of the Bethe roots, as integrals, as complex integrals of some Bethe kernel. So here comes integrability. You express your correlation function as a big, but a finite, integral, complex integral, which in fact is nothing but the Bethe ansatz. So this is a formula which comes from Bethe ansatz, but you can forget about Bethe ansatz. Once you have the formula, you can just prove that this is true. You can just prove that the right-hand side of your formula, which you have constructed using Bethe ansatz, in fact solves the dynamics of your problem with the right initial conditions. So in fact, this is one of the rare cases I know where the Bethe ansatz is perfectly exact. Okay? There is no asymptotics, there is no assumption about completeness. Everything is just proved mathematically. The formula, the right-hand side, is equal to the left-hand side. So although you use integrability and Bethe ansatz, you don't have all the caveats that you have usually of completeness, of looking at the roots and localizing them and so on. Here it's a perfectly kosher formula, but the complexity is that you have to take integrals in the complex planes of some complicated kernel, and the integrals have to be on some nested contours, and the contours have to be chosen according to the initial condition. So it's slightly, but once you have done that, there is no cheat. So there's a second step, the so-called integrable probabilities, using Bethe ansatz to compute exactly some transition probabilities. Now comes the next step. So I'm not going to prove it, but the proof is, in fact, once you have guessed the formula, the proof is simple, because you just have to somehow substitute this huge formula into the dynamical equations, and there will be some simplifications in the numerator. You use Cauchy formula, and you prove that thing vanishes. So it's just simple identities on these kernels which allow you to prove the fact. Yeah. So as you may know, in the case of KPZ, there are a few conditions that have been solved. So here it's only for the step or flat. We may extend it to some other initial conditions, but a very restricted class. Yeah. Not Hamilton, it's Markov, but yeah. Yeah. Yes, so first you say that these correlation functions satisfy a closed set of equations. These closed set of equations are nothing but the Markov equations for an integrable model, which turns out to be the exclusion process itself. Being integrable, you can write the transition probabilities or the states of the system by Bethe-Ansatz. In principle, Bethe-Ansatz allows you only to diagonalize your system, and you should do the synthesis to make the evolution, and here it can be done. So you can resum the Bethe series somehow to get the real transition operator, not only the eigenvalues, but you can decompose the initial state into each of the eigenvalues, resum them, and get the time-evolved state after a given time. Okay? Yeah, this is the exact solution at a given time t. And time t appears here. So it's resummation, it's a Fourier synthesis of your Bethe states, if you want. So the Bethe comes from here. Bethe, if you're familiar with Bethe-Ansatz, you recognize these kind of kernels. Okay? If you're not familiar, you don't care. I just give you the formula and you check it works. So yeah, this is the key point, is that usually Bethe-Ansatz, like in quantum mechanics, you only compute the eigenvalues and the eigenstates if you're lucky, but here you can really resum them. You can really make the Fourier synthesis. Okay, so that's the second point. The third point is I told you that in fact we're interested in the symmetric case, which is tau going to 1. And for tau going to 1, we don't have this duality. So somehow we have now formulas for tau different from 1, and we have to take the tau going to 1 limit. So this is a bit combinatorial and tricky part to compute these integrals. There are many poles, so somehow you have to eliminate the poles and write some recursion formulas. So this becomes a bit frightening, but okay, stay with me. So you can rewrite this integral as a sum over poles with some contributions and so on and so on. And in the end, you end up with some nice looking series where these kind of integrals are involved. So you can take the symmetric limit, and now you get these kind of integrals, which again very much look like the symmetric Bethe-Ansatz. I mean, if you're familiar with SU2, XXX, spin chain Bethe-Ansatz, this will probably ring a bell, this kind of kernel. Okay. So the last step is that you have a series now for this characteristic function involving these kind of integrals, and the series, or each type of these integrals, which is a product of a symmetric about some permutation and so on, you can symmetrize it and rewrite it as a determinant. So this is one of the magic also, is that there are plenty of magic things happening. This kind of integral, in fact, is a determinant in disguise. But a determinant of n by n determinant at order n. And now you can resum this and identify it to a Fredholm determinant. So, okay, this is the end of the technical part. I just wanted to show you rapidly how things can be done. And now we can start talking about physics and probability distribution, cumulants and so on. We can go back to the tracer. Where is it? Here? Here, so the epsilon of psi is just, in fact, the random walk thing. Where did I hide it? Sorry, it's here. So it's just, cos theta. I mean, going right, going left, minus twice staying in the same place. So it's just the propagator of a single particle. Okay, so let's come back to the tracer. So we now have a formula for this height distribution, and yes, so the thing is that this is okay, but it's only in the symmetric limit that these horrible looking complex integrals collapse into that one. Otherwise, it may be possible to do something, but we didn't see. Yeah, this is a very good question. Okay, so as I told you before, if we know the statistics of the heights, or the probability distribution of the heights, we can deduce the probability distribution of my tracer. Simultaneously, both the tracer position and the height variable satisfy a large deviation principle, thanks to Vasan and Setoraban. Or for physicists, maybe we could just postulate that it's true, but they proved it. So in fact, by taking these two facts together, we can find a simple relation between the large deviation function of the tracer, which is the basic object I'm interested in, and the large deviation function of the height variable, which is the object we just computed, okay? Or we computed its Laplace transform. And we end up with this neat formula that the large deviation function of the tracer is the maximum with respect to lambda of the characteristic function of the height variable. And this characteristic function, I gave you, at least I flashed a very explicit formula here in terms of error functions and so on and so on. So the large deviation function of the tracer is fairly explicit. Okay, you have some error functions involved, but it's a fairly explicit formula. And now that we have it, we can compute things, or we can compute some properties. For example, in the StatPhys community, people are very much interested in the symmetries and in the so-called Gallavotti-Cohen relation. You can prove that it is true here. So this Gallavotti-Cohen relation, which is valid far from equilibrium, is a huge extension of the fluctuation dissipation relation, of Einstein relation. It implies Einstein relation close to equilibrium. When it was known by these people a long time ago that the Einstein relation is true close to equilibrium, where your asymmetry is very little. Well, here we can prove it in general terms, even very far from equilibrium, because we have an explicit formula. Again, using this large deviation function, we can retrieve known results and compute higher cumulants. I told you that the variance was computed by Aratia 35 years ago. Well, if you take the explicit formula I showed you before, you can retrieve it. But you can get the 4th order, or you can get the 6th order. And I didn't write the 8th order, because it's too long. But you can get any cumulant to any order. And again, these formulas are exact. This is in the large time limit, but they are exact formulas. There is no approximation. Yes, because of this large deviation principle. You can plot the large deviation function explicitly compared to the free case. You can compute, if you start with a step initial condition and put your tracer here, because of the step initial condition, your tracer will have an average drift. So you can compute the speed of this drift. In fact, it's a drift which is in square root of time. So you can compute this coefficient. You can compute the fluctuations, and so on and so on. So there is plenty of physics that you can get from these explicit formulas. You can be interested also in this special setting where all the particles are on the left and nothing on the right, and you can compute how much current has crossed from left to right from time 0 to t. You can retrieve this result, which was derived a few years ago by Derrida and Gershenfeld as a special case of our general formula. And you can go also to the continuous limit, where you replace your exclusion particles by Brownian motions that reflect to each other, Brownian particles which are not allowed to cross. So you just exchange when they, you use Snell's law to reflect them when they touch. And you can take the continuous limit of the formula and get a pretty neat explicit expression of the large deviation function in that limit, involving, again, integrals of error functions. in the case of Brownian particles. So this is a large deviation for Brownian motion. There are some special cases again. I mean, I hope that Sanjeev would be here, but he's too busy. There is a calculation he did a few years ago in some case where you have Brownian particles on the left-hand side and emptiness on the right-hand side, and you look at the maximum of these Brownian motions, of the extreme value statistics of these Brownian motions. If you take some special case of this formula, you retrieve Sanjeev's results, and so on. So, okay, I mean, we are quite happy with this result because we solved a kind of explicit problem, but I hope, or I don't hope, that I convinced you that it's quite technical, and it's, in fact, the details are quite complicated and horrible. So maybe we should try another approach, which is in the spirit of these lectures of Professor Abanov, and maybe we should just forget about all these horrible combinatorics, better ansatz, and so on, and try to do something else which is more physical. So that's the second part in the last 10 minutes of my lecture, but it's shorter. Let's try to do a hydrodynamic description to get some of these results, or hopefully all of them. We will not get all of them. Better ansatz is still stronger. So if we were to do a hydrodynamic description and look things from away, what will these kind of models look like? Even more generally, we have a bar of conducting material which connects two reservoirs, and inside the bar, particles are driven either by an external field, I can add an external field if there is some asymmetry in the hopes, or by the difference of potentials or densities between the left and the right reservoir. And the bar is of length L. So this is the coarse-grained vision of these kind of models. So if we start from the microscopic level, we can try to define a local density of particles by taking boxes, and a local current, again referring to your set of lectures in the last days. And in that case of the exclusion process, you can prove, great people have proved rigorously that the hydrodynamic limit is achieved. So you can, as a physicist, you could write in a kind of very naive way that you have conservation relation in the bulk. So dt rho over dt, d rho over dt is minus the divergence of a current. And the current is due to a local gradient and some external field multiplied by some conductivity. But this is a mathematical result, and this is a great mathematical result, which has been the collective work of many people, but the prominent name in these hydrodynamic limits is, of course, Varadhan. So people around Varadhan proved rigorously the existence of this hydrodynamic limit. And this is one of the very few cases where this proof is rigorous and complete. Okay? But this tells you that if you start with any given profile of densities at time t equal to 0, and you make it evolve according to this PDE, you will get the average profile at time t. But this gives you only the average behavior. And we are interested mostly in fluctuations. And this deterministic equation does not embody fluctuations at all. So we need to go further. We need to take into account stochasticity, randomness. And this was done more recently, mostly in the physics community, and this comes from under the name of macroscopic fluctuation theory. There is a whole large deviation theory behind that, which is an extension of the Freidlin-Wenzel small noise theory to infinite systems with an infinite degrees of freedom. I'm just going to give a kind of very hand-waving understanding of it, but there is a rigorous theory behind it. The idea is to start from the previous equation. I will forget about the external field because I'm interested in the symmetric case. So nu is equal to 0. So it's to start with the previous macroscopic deterministic equation and to add to it some noise. So again, written like that, it looks non-rigorous, but there's a rigorous way of arriving at that. Okay? And the one difficult thing is that the noise you add is a multiplicative noise, and the amplitude of the noise is, in fact, proportional, is equal to the conductivity of the system. So now you have a fluctuating stochastic PDE that describes your system, and the noise is small. The noise amplitude overall scales as one of the size of the system. So to wrap everything, if I want to understand the large-scale behavior of the system, I just write this stochastic PDE, okay? And the only thing I need to input from the microscopic dynamics is the diffusion constant, d of rho, and the conductivity sigma of rho. Once somebody gives them that to me, or I compute them, I can go to macroscopic and forget about microscopic dynamics. Of course, it can be very difficult to compute these transport coefficients knowing the microscopic dynamics. It can be impossible. In the case of the exclusion process, it's quite easy. D is 1 and it's constant, and sigma is 2 rho 1 minus rho. But for more general models, I'm not going to go into the details, but you can play with plenty of models and try to compute these transport coefficients, and they can start looking ugly. There are even more ugly examples than that. But once you know these transport coefficients, you can a priori forget about the underlying macroscopics and go to macroscopic immediately. Okay, so now that you have this stochastic PDE, you can write a path integral for it. So you can write an action. This is precisely what was done by the group of Gianna Lasigno in Rome when they developed this macroscopic fluctuation theory, and they were able to show that the probability distribution of seeing a current profile and a density profile in your system during some amount of time takes a large deviation behavior with an effective action, and the effective action is given by an exact variational formula, which again involves d and sigma. And in fact, if you look at it, this is nothing, in a very naive way, saying that j plus d gradient of rho divided by square root of sigma is a white noise. So this is nothing, if you do it in very unkosher way, than writing the white noise measure, chi square, okay? So it amounts to that. So now we have an action at the macroscopic level. And what we have to do is, for example, if I'm interested in tracer dynamics, we have to understand how to relate the tracer position to macroscopic variables. Macroscopic variables are the density field and the current field. Well, in fact, it's quite easy to relate that. You just say that the number of particles between the tracer and plus infinity is equal to is constant, because the tracer cannot overcome the particles to its right, okay? So it's a way of writing the tracer position as an implicit functional of the density at time t and at time 0. So finally, what we have to do is, if we want to compute the probability of seeing a given tracer position at time capital T, we have to find the optimal fluctuation according to this action that generates a given fluctuation of the tracer position. So forget about everything. It's a problem in classical variational calculus, in classical mechanics. I have an action, I have a constraint, I want that something happens, I want my tracer to go there, I want my current to have this value, I want any observer you want to have this behavior. I have an underlying action, so I have to optimize my action under the constraint, okay? And if I do that, I end up with the so-called macroscopic fluctuation theory equations, which is a set of two coupled non-stochastic, because now I am optimizing an action with respect to small noise. So I end up with two non-stochastic field equations for two fields, Q and rho. So rho, Q and P, sorry. Q is mostly my density field, and P is a conjugate field to it, which involves the current, but it's not the current. And the optimal equations for the previous action, in fact, they are Hamiltonian equations. So I'm ending up with an effective Hamiltonian dynamics for two conjugate fields, which satisfy two Euler-Lagrange equations, and my constraint on the tracer position and so on will be embodied as a boundary condition for these PDEs. So it's hydrodynamics. So I still have 10 minutes. Yeah. So it's hydrodynamics. Okay, we have completely washed out Bethe-Ansatz, combinatorics, and so on, and restate the problem in purely hydrodynamical terms, again in the spirit of the lectures we had in the previous days. Okay. So this looks very nice, and this looks very much like, you know, coupled diffusive equations, hydrodynamics, and so on. But there is a huge caveat. In fact, nobody has been able to solve these equations in non-trivial setup. Okay? These macroscopic fluctuation theory equations, if you really want to get a non-trivial solution which depends on time and with some non-trivial initial condition, we don't know how to solve them. But okay, this is not the sad end. At least we can do some perturbation theory. We can do perturbation theory, for example, with respect to this fugacity that appears in the characteristic function. Okay, so P is the density field. In fact, the thing I didn't do, this is Lagrangian. I go to Hamiltonian. This is a Lagrangian problem. I go to the Hamiltonian formulation. So, and going to the Hamiltonian formulation, Q remains rho, but P is the conjugate variable with respect to this Hamiltonian. So it would be the same for P equal to 0. It would be the same, yeah, in the case of P equal to 0. Because P somehow embodies the non-equilibrium, the constraints, yeah. So in certain special cases, if you forget about that, it will be the same. Yeah. Somehow P is a kind of the effect of the noise in your problem, which is a deterministic variable. So one thing you can do with these equations is to do a perturbative study. You can compute the cumulants exactly perturbatively using these equations. So this is something we did in the last few years. And for example, you can retrieve the formula, the Aratia formula for the second moment, and you can also get a formula for the fourth cumulant. And this is in fact the same formula that we got by Bethe-Ansatz. To put things in context, this was done before, and also done by Abhishek's group independently. So this was done before, and it was a good check for our Bethe-Ansatz calculations, which are complete and exact, which allow us to get the next cumulant. The sixth cumulant is not possible to get by this perturbation theory. It becomes too complicated. But at least you can do something. Another thing you can do, so I told you it's not easy to solve these equations in the general case, but if you look at the Brownian particle problem, reflecting Brownian motion, then these equations, using the Hopf-Kohl transform, can be linearized and can be mapped to the heat equations, to two coupled heat equations. So in the case of reflecting Brownian motions, these equations can be solved exactly, even with time-dependent dynamics. And this is quite nice because this allows you to compute a large deviation function, but better than that, this allows you to have a space-time picture of what's happening. So we are now having reflecting Brownian motions, we have a tracer somewhere, and we want this tracer to do some excursion, to have some anomalous fluctuation. So then in that case, the density profile of the system has to conspire so that your tracer does some non-typical fluctuation. Okay? And this macroscopic hydrodynamic approach allows you to picture and to see how the shock wave allows your tracer to do some non-typical excursion. Okay? For example, here we put the tracer at position 0, at time t equal to 0. If we want this tracer to go very far, much further than typical behavior on the right, well then the initial conditions has to be tuned so that we have an over density behind the tracer and a kind of hollow state in front of it. So this is a blue initial condition. And then of course the tracer will go away and there will be an overshoot. It will push the particles in front of it and there will be an overshoot of density in front of it. So if I were better in tech, I could even show you a picture, a dynamical picture of the hydrodynamic wave profile, which allows you the whole system to produce a non-typical fluctuation. This is totally beyond calculations of better ansatz. This cannot be reached by better ansatz. So the two approaches are somehow complementary. Okay, so I now go to the conclusions. Amy, how much time do I have left? 5 minutes? Yes, large enough. So again, taking some more perspective, if we look at systems out of equilibrium, which is the typical picture is to make, again, a bar of metal between two reservoirs at different temperatures or potentials. We know from linear response theory that we'll probably have, thanks to the heat equation, a linear profile on average. And we also know that the linear response current will be given by Ohm's law or by any formula you like, Poiseuille, Fick, whatever, let's say Ohm's law. But of course, all these things fluctuate. And when we do statistical physics, we're interested in fluctuations. And two questions we may ask is what is the probability of seeing a non-typical profile? For example, this red profile. Or what is the probability of seeing a current which is 5 times bigger than the ohmic current, or 10 times less? What is the distribution of this current? So it would be perfect to have the full distributions, but at least if we have the large deviation functions of this profile and this current, we would be happy. This would be a non-equilibrium information. More generally, if we were able to compute the probability of seeing during a certain amount of time a certain current profile and a certain density profile in my system, it would be a great, great information on the non-equilibrium behavior of such a system. And one can show, generally speaking, that this takes a large deviation form, so that everything is embodied in this rate function of the two fields, rate functional of the two fields J and rho. So if I had a hold on this rate functional, if I had a way of computing it, I would understand the non-equilibrium behavior of my system. By the way, if you think about that, it's very similar to a kind of Boltzmann type of ansatz. But here there's no energy. The role of the energy is played by this large deviation function, and the distribution of configuration is now a probability distribution on some functional space. Okay? So what Jonalazino et al. Tell us is that for certain type of models, which are driven diffusive models, you have a variational ansatz for computing this rate function of these two fields. And these fields satisfy coupled PDEs, nonlinear PDEs. Okay, so that's a general framework. Now if we take the other strategy, if we look at this model, general picture, we can model it by the exclusion process and try to do exact combinatorics, better ansatz to compute the corresponding observables or the large deviation functions for this exclusion process. Okay, so that's the integrable strategy. And indeed, there have been 1,000 articles on this exclusion process in the last 20 years, and many, many quantities have been computed for this model. For example, I told you today about the tracer dynamics, but the full quantic statistics of the current through this model has been computed exactly also. And Fabian and Jan de Geer were involved in that 6-7 years ago, and simultaneously we in Saclay also did similar calculations. So the full quantum statistics for this problem takes this rather simple form. And there are plenty of other things that can be computed. So to go to the full conclusion, so this is the integrable point of view. The hydrodynamic or the MFT point of view is much more general. It's hydrodynamics. A priori, it does not rely on integrability. The only input from microscopics is this diffusion D and this conductivity sigma that you have to compute for microscopic dynamics, and it can be hard, but once you have them, you can forget about microscopics. And this leads to Hamiltonian set of equations that are nonlinear and coupled. And a priori, this seems to be very versatile. Unfortunately, these equations, the only non-trivial solutions that we know for these equations at the moment, they have been obtained using exact integrability on some microscopic models. So you see there is a kind of interplay between the two approaches. Of course, for these equations, people who are versed in plasma physics, hydrodynamics, can do asymptotic matching, WKB, perturbation theory, and so on and so on. The whole techniques that are available for Navier-Stokes or for Euler equations can be applied to these kind of equations. And there's a whole group in Israel around Baruch Merson, which is playing this game for these equations. So last two questions. So we have now a nice set of PDEs at the macroscopic level that, for example, in the case of the exclusion process, are coming from an integrable model. Is there any chance that these equations are themselves classically integrable? It would be nice, because then we could use inverse scattering theory for these equations and forget about microscopic meta-ansatz and look at solitons for these equations or exact solutions. So this is one way of exploration which is quite nice. And in fact, the analysis of this new set of nonlinear hydrodynamic equations has just begun, and people are getting involved more and more. Thank you for your attention.
I have a comment slash question. So if you're interested in the leading probability of these large fluctuations, and you really do not need to know exact solution, you need to know only its asymptotics. Because if you substitute the solution of equations into the action, then it basically goes to boundary.
Yes,
but you have to fix the coefficients in these asymptotics, and that's a difficult problem. So is it?
Yeah. In fact, what I want to compute is not the leading probability, it's a full large deviation function.
Okay.
And for the full large deviation function, I do need a full solution. If I want only to have the large deviation function around its bottom and get, the first few moments.
So you want to have the shape of optimal fluctuation?
I want to have the full large deviation function.
Yeah.
Then I need a full solution.
I have a question about the hydrodynamic MFT equations. So you said that you need to impose some certain suitable boundary conditions, right? So what's the precise meaning of them? Boundary conditions.
In fact, everything is hidden there, and I voluntarily put it under a rug. I mean, it would, for example, I gave a full 1 hour talk about this hydrodynamic point of view, and then I go into the details. So in fact, you see, first of all, there's a minus here. If you see a heat equation with a minus, you should come here and just hit me or kill me. It blows up in finite time. Okay? So in fact, the boundary condition is not a Cauchy condition. You see, you have two fields, and it's a second order PDE. So you have 4 boundary conditions. To make it well defined, you need 2 boundary conditions at initial time and 2 boundary conditions at final time. Okay? And they are mixed. So there are 4 of them. And the 4 of them, they embody the initial condition. So 2 of them embody the initial condition. And 2 of them, in fact, embody the fact that you want your tracer to do some non-typical excursion. The non-typical excursion, there's plenty of things hidden, can be traded off as a special value of the fugacity parameter, here, for example, or here. Let's see, here. If I want my variable n to do a non-typical excursion, it amounts of tuning the fugacity parameter, the Laplace parameter, to a non-typical value. Okay? And this non-typical value of the Laplace parameter also enters as a boundary condition in my MFT equations. So it's quite contrived.
Thank you very much.
Thank you for the question.
Okay. Any other questions, comments? Well, if not, let's thank the speaker for a very nice talk. So we break for lunch.